Okay, now we're going to look at question 2, but I got to go back here. The number I have here is not 1% different than this number. It's more like 0.1% different, but I believe this number is miscalculated and should be, I think, 10% greater than this would be 1.583 joules. Now you can calculate that and corroborate it, but there is an error there. And I emphasize that by writing the 0.1583 joules. Again, compare that. I'm doing that in my head and it's late. And a 0.1%. Well, no, that would actually then be a 1% difference, as it must be, because clearly the extra 8 out of 800 is a 1% difference in the change in the Y position. Now we have a situation where we have a pendulum. A mass on a spring, mass on a spring. And when we add 2 newtons to whatever's on the spring, it stretches an additional 10 centimeters, meaning that the force constant is, well, it's the change in the force divided by the change in the position. I'm using Y instead of X for the position of this oscillator because it's moving up and down, and we more naturally think of Y as the position. In any case, if we divide this change in force by the change in position or change in length of the pendulum, we get 20 newtons per meter, and that's the force constant for the pendulum, because the force constant is the constant you multiply by the change in your pendulum length to get the change in the force on the pendulum. This means then that relative to the zero position, if Y is measured relative to equilibrium, the net force is negative Ky, where K is 20 newtons per meter. Now the question is, we add a 5 Newton weight, and I'm approximating, it says 200 grams, 500 grams. That's approximately 2 newtons, approximately 5 newtons, with only a 2% error in that assumption. What happens? Well, if I was to add the 5 Newton weight and let the pendulum stretch a little more, it would stretch out to a point 25 centimeters below that point, because an extra 5 newtons at 20 newtons per meter will stretch the spring an extra, well, 5/20 or 1/4 of a meter. Now you can write that out formally, and you probably should, but intuitively, if you get 20 newtons for every meter of additional stretch or length, then to get 5 newtons you only need 1/4 of a meter. And 20 newtons per meter, it just means exactly what I said. If you add 20 newtons, you're going to stretch it out by an extra meter. That gives you a new equilibrium position when you have the additional 5 Newton weight that's 25 meters below the point you get if you add the 200 newtons. Okay, so you've added 200 newtons, measured the force constant. Now we add another 5, so we've added a total of 7 newtons, 700 grams. And now, instead of letting it come to equilibrium, we're going to take the thing at its equilibrium point with only the 2 Newton force on it, 200 gram mass, and we're going to add a 500 gram mass, giving us a total mass of 700 grams. But now, as soon as I release this, we are 25 centimeters above the equilibrium point. So, what does that tell us? Well, here we are, 25 centimeters above the equilibrium point, releasing from rest. So we're 25 centimeters from equilibrium on a pendulum with this force constant and a total mass of 700 grams. The potential energy at that point is 1/2 Ky squared. Y is now, relative to the new equilibrium position, 25 centimeters, 1/4 of a meter. Y squared will then be 1/16 of a meter squared, multiplied by 1/2 K, K being 20 newtons per meter. We get 20 newtons per meter divided by 32, well, It's going to be divided by 32 because you have 1/6 of the y squared. It's going to be newtons per meter for the k, and meters squared for the y. And we're going to end up with 20, 30 seconds, or 5/8, or 0.625. And it's going to be Newton, meters, joules. And you can work out the details of that. They're very straightforward. Now we can put this information into the form of a solution to a simple harmonic oscillator, okay, because we have the negative ky rule. We know that if we do m y double prime equals negative ky and solve it, we're going to get the solution with an omega equals square root of k over m and all that stuff. So what do we know? We know now y of 0 is 25 centimeters, and we know that the velocity at that point is 0 because we're going to release it from that point. Again, we're at position 25 centimeters because we're 25 centimeters above the new equilibrium position, the position at which this 700 grams would remain stationary. Y prime of 0 equals 0 tells us, well, y prime is our velocity. That's our v of 0, which is y prime of 0, and that's 0 because we're releasing it from that position, at that position, from rest. Omega is just square root of k over m. Mass is 700 grams or 0.7 kilograms. K is 20 newtons per meter. We divide that out, and we get something pretty close to square root of 28 newtons per meter, a little more than 28, and that square root, I'm pretty confident, is going to be 5.3. More than 5.2, less than 5.4. It might be 5.4 now that I think about it. So it's between 5.3 and 5.4, I believe. So you can figure out where it rounds off. Omega is approximately 5.3 radians per second, whatever you get from the square root. So now what do we have? We have a pendulum, or a mass in a spring, oscillating in simple harmonic motion. Its total energy is 0.625 joules, and that is its potential energy at the 25 centimeter position. That is also its kinetic energy at equilibrium, because at equilibrium its potential energy is 0. That potential energy being 1/2 kx squared, x is, or in this case, 1/2 ky squared. At equilibrium, y is 0. So there's 0 potential energy, so all that potential energy it had at 25 centimeters is now gone, and it has a kinetic energy equal to its original potential energy. So this 0.625 joules is the potential energy at 0.25 centimeters. There's 0 kinetic energy there. If it goes down to the 0 centimeter position without any non-conservative forces, any external forces acting on it, all that kinetic energy, potential energy, is going to be there as kinetic energy, which means that we could easily calculate then the maximum velocity without having to get the equation of motion. And the maximum velocity we get from that calculation should match the maximum velocity we get from the equation of motion, and the velocity equation. And that is also equal to the total energy, which is the potential plus the kinetic energy at any point. The key being that the net force is just the spring force. Okay, now there's gravitational force and there's spring force, and they go together, in effect, to give you the potential energy change. But you can treat this just as the potential energy due to just the spring relative to the equilibrium position. We talked about that a little bit, and I could go into more detail, but I don't have time right now. And I think we talked about that to everyone's satisfaction. Okay, so this pretty much gives us all the information we need to answer all the questions in question number 2.